Hi everyone, it's Kevin and Alex, and welcome to our crash course on the chaos in material science. So we're just going to dive straight into things and talk about the order and chaos in materials. While doing some research, we stumbled on this quote which we think is a good gateway into what we plan on talking about. So this guy Srikanth Patala said this about materials. Most materials have a particular atomic structure that is fairly regular. For example, aluminum has a cubic structure, with atoms that line up into long chains of cubes, whereas titanium forms into what are basically stacks of hexagons. But when two materials meet, such as in a metal alloy, these tidy, organized structures clash with each other, creating the disordered grain boundary.
For those of you who have no idea what that quote meant, let's give you some background. As you know, materials are literally everywhere. When trying to study them, there are three different levels to examine. Level 1 is the macroscopic level, and it's what you can see with the naked eye. As you go down, the microscopic and atomic level require some type of equipment to view. And lastly, the atomic level is composed of atoms and structures such as cubic or hexagonal, like the one shown on the previous slide. What's really cool about all of these, though, is that they make fractals or fractal-like shapes. So at level 1, the best example of this is in natural materials. Rivers, mountains, trees, clouds, and much more have some form of a repeating pattern. Going down a level, we have ice crystals and dendrite growth, which is what we'll be explaining more throughout the rest of this presentation. And on the third and final level, there's the unit cell. This one isn't quite a fractal because it does not have a self-similar pattern at different scales, but we thought to include it because it does repeat in all directions almost infinitely. So when looking at a crystal structure that's filled with unit cells, it almost appears to look fractal-like.
Dendrites can form in a metal at the start of the solidification process. We will go into more detail about the mechanics of this in the next slide, but first we want to pique your interest with some cool images of dendrites. These first pictures are 2D images of dendrites that are fully grown, but they do not just grow in two dimensions. They grow out in all dimensions and have what are called primary, secondary, and tertiary arms. This fractal-like growth appears ordered, but when looking at the colorful image, the growth of them together has a chaotic nature. In class, we learned about finding the fractal dimension, but in the real world, fractals are not infinite. This pattern only repeats a few times, and unlike some of the cool fractals we learned about in class, this one has a finite area and volume. That is why we call it fractal-like.
The way material scientists understand how things work or move or how anything functions is by determining the driving energy. In other words, what is making this action happen? In the case of dendrites, it's something called Gibbs free energy. I know many people in the class have not been exposed to this, so the main thing to take away is that there are a lot of variables involved. Temperature, surface energy, cooling rate of the metal, the size of the container, these are all things that affect the Gibbs free energy. And this energy controls how the dendrite will grow. So theoretically, this should be a deterministic thing. There are a lot of variables, and if we know them all, then it should be possible to create a model. However, just like the Lorenz model and him making weather predictions, this isn't the case. Assumptions are made, and the model is actually just a simplified version of what's really happening. Another interesting thing to note is many times during solidification, dendrites grow in a preferred orientation at the start, but eventually begin to form in all directions. So on the video, you can see that dendrites are forming vertically, but then as it reaches the halfway point, they start forming in random directions. So at this point in the video, you may be wondering, why the heck do we care about predicting dendrite growth? And that's a good question. The answer to that is, depending on the final structure, different material properties such as strength of the material are affected. Like you saw on the slide before, dendrites all going in the same direction will react differently than dendrites going in random directions. Modeling the growth and predicting the final result can be very useful when trying to engineer a stronger metal.
Since the origin of these models, there have been many simulation softwares released, becoming more accurate over the years. One popular software, Moose, can model the growth during different time intervals and produce a final outcome of dendrite formation. Some models focus on creating a precise model of a single dendrite, like the image on the bottom left, while others will focus more on the growth as a whole, like the image on the bottom right. And many times, there's a happy medium, like the image in the center. These softwares use a variety of equations, which often get complex very quickly. It is often too difficult to measure the Gibbs free energy at every single point on all of the arms. So while some models use Gibbs free energy, most will take shortcuts and model using pressure and velocity instead. One paper we read about used these two equations to iterate the two fields. There was limited information, but we will explain what is happening to the best of our ability. This example uses the finite element method for its calculations. What this method does is that it starts the model at a preset state, and this state is designated as the starting iteration. Then to calculate the next iteration, it applies the equations shown in the brown on every node in the system, using the current state as the input parameters. This process is repeated over and over until the number of iterations desired is met and the model is complete. And just to wrap things up, we've included our references that we used in this project. If you made it to this point of the video, I hope you learned something and have a great rest of your day. And that's all, folks.